You write code in C, but your computer only understands machine language. So who does the translation? The compiler. But here's where it gets interesting. Sometimes the compiler runs and the program runs on the same machine. And sometimes the compiler runs on one machine but creates code for a completely different target system. That is exactly what we'll understand today. Hello everyone, welcome back to the channel. In today's video, we are going to understand an extremely important concept in programming and embedded systems, and that is the compiler. If you are learning C programming, Linux, or embedded systems, then this topic is one of the foundations you must understand clearly. In this video, we will learn what a compiler is, why a compiler is needed, how a compiler works, what is a native compiler, what is a cross-compiler, what is host and target, and real examples using Linux, G, C, Keil, Aware, R, PIC, and ARM. So let's begin from the very basics. What is a compiler? A compiler is a software tool that converts a program written in a high-level language into machine language. Let's understand this slowly. When a programmer writes code, they usually write it in a language like C. For example, a programmer may write a simple line such as printf, hello world. This type of code is readable for humans. But the processor inside a computer or microcontroller does not understand C language directly. A processor understands only machine instructions, which are basically binary instructions made of zeros and ones. So there must be something that translates human-readable programming code into machine-understandable instructions. That translator is called a compiler. So in one simple line, compiler equals high-level language to machine language translator. Now, the question is, why do we need a compiler at all? Why can't the processor directly understand our C code? The reason is very simple. Processors are electronic devices. They do not understand English words, C syntax, loops, functions, or variables the way humans do. They understand only very specific machine instructions. For example, an x86 processor understands x86 instruction format. An ARM processor understands ARM instructions. An AVR controller understands a VR instruction format. An 8051 controller understands 8051 machine instructions. That means, every processor needs code in its own machine format. So when we write code in a friendly language like C, we need a compiler to convert it into the exact instruction format required by the processor. Without a compiler, the processor cannot execute the program. Let's understand it with a simple analogy. Imagine you speak English, but another person understands only Japanese. Now if you want to send a message, you need a translator. The translator converts your English into Japanese so the other person can understand it. In the same way, the programmer writes in C. The hardware understands only machine language. The compiler acts as the translator. So the compiler is the bridge between the programmer and the processor. Now let us understand the basic working flow. First, the programmer writes the source code in a high-level language like C. The compiler checks syntax, variables, functions, structure of the program. The compiler converts that source code into lower-level machine instructions. The output may be executable file, binary file, object file, HEX file, depending on the system, and target hardware. So the overall flow becomes source code to compiler to machine code but not binary output. This is the fundamental job of a compiler. Now let us connect this concept with a real system. Suppose you are working on a Linux machine. You write a C program, then you compile it using a compiler such as GCC. Your system may look like this. Operating system is Linux, hardware is x86 or Intel processor, and compiler is GCC. In this case, you write the program on Linux, the compiler runs on Linux, and the compiled program also runs on Linux on the same machine. This is a common desktop software development case. So the compiler is running in one environment and producing executable code for the same environment. This leads us to a very important concept is native compiler. Before native and cross compiler, we must understand two terms, host and target. The host is the system on which the compiler runs. In simple words, the host is your development machine. For example, your laptop, your desktop, your Linux PC. The target is the system on which the final compiled program will run. Sometimes the target is the same as the host. Sometimes it is completely different. This difference between host and target is the key to understanding native compiler and cross-compiler. A native compiler is a compiler where the host and target are the same. That means the compiler runs on a system and it generates code for that same system. So here, host equals target. For example, compiler runs on Linux x86. Generated executable also runs on Linux x86. That is called a native compiler. Both host and target are same program is implemented and executed in the same machine. That is exactly the definition of a native compiler. Native compiler example. A good example is GCC running on Linux and generating code for Linux x86 Turbo C in a same system setup. In both cases, development and execution happen in the same environment. Let us imagine the flow of native compiler. Programmer's Linux PC consists of compiler runs here. Executable generated here. Program also runs here, in the same system. No change of processor architecture. No change of execution platform. That is native compilation. This is usually easier to understand because the build machine and execution machine are the same. Now let us come to the most important concept in this video. A cross-compiler is a compiler where the host and target are different. That means the compiler runs on one machine but it generates code for another machine. So here, host not equals to target. This is called cross-compilation. This is extremely important in embedded systems. Let's think about an embedded system like 8051, AVR, PIC, ARM microcontroller. Can you directly write and compile code inside those tiny microcontrollers like you do on a desktop PC? Usually, no. Why? Because most embedded systems do not have a full keyboard, a large display, full operating system, full development tools, enough storage or interface for compiling like a PC. So what do? We use a host machine, like a laptop or desktop, PC, to write and compile the code. Then the compiler generates machine code for the target microcontroller. That generated file is then loaded into the controller. That is why cross-compilers are used. Suppose you have host machine is Windows PC or Linux laptop, target machine is ARM microcontroller. You write the code on your PC. The compiler also runs on your PC. But the code is not meant to run on your PC. It is meant to run on the ARM microcontroller. So the compiler generates ARM machine instructions, not x86 instructions. That is a cross-compiler. This is completely different from native compilation. This is why cross-compilation is the heart of embedded systems. In embedded systems, the development environment and execution environment are different. So embedded development usually depends on cross-compilers, target-specific tool chains, hex or bin files, flashing or programming tools. Here another important topic is why one binary cannot run everywhere. A binary made for one processor usually cannot run on another processor. Why? Because processors have different instruction sets. For example, x86 instructions are different from ARM instructions. ARM instructions are different from AVR instructions. AVR instructions are different from 8051 instructions. So if you compile a program for x86, it will not directly run on ARM. If you compile for AVR, it will not run on PIC. That is why the compiler must know the exact target processor. This is also why target selection is very important when building software for embedded systems. One more important clarification about difference between IDE and compiler. They are related, but not exactly the same. The compiler is the tool that translates code into machine-level output. Coming to IDE, An IDE, or integrated development environment, is the complete software platform that may include code editor, compiler, linker, debugger, project manager. Examples like Keil, MPLAB, a VR studio. So, IDE is the full environment. Compiler is one major tool inside it. So let's quickly revise the entire topic. A compiler converts a high-level language like C into machine-understandable code. A processor cannot understand C directly. That is why we need a compiler. If the compiler runs on a system and generates code for that same system, it is called a native compiler. If the compiler runs on one system and generates code for another system, it is called a cross-compiler. Cross-compilers are especially important in embedded systems because the code is usually developed on a PC and executed on a microcontroller. And that is why understanding host and target is essential. If this video helped you understand the topic better, make sure to like the video, share it with your friends, and subscribe to the channel for more content on programming. Thanks for watching, and I'll see you in the next video.